This visual mnemonic presents the mechanism of action of anti-seizure drugs, a crucial aspect of neuropharmacology. Recall, in our previous video, we introduced and classified anti-seizure drugs. In this video, we'll picturize the mechanism of action of these drugs. Next, we'll delve into the mechanism of action of anti-seizure drugs. In this dimly lit room, we'll explore the different types of mechanisms and examples of drugs that fall under each class. The dim lighting represents the inhibition of sodium channels, a key mechanism of action for many anti-seizure drugs. The room is so dim, sodium inhibition. Learn to associate these two together for easy recall. Let's take a closer look. Inhibition of NOD channels works by blocking the channel when the Na gate is opened, prolonging the opening and leaving it in an inactive state. This makes the channels refractory to stimulation. Examples of drugs that act via this mechanism are illustrated by the objects in and around the room. The fern leaves outside the window represent phenytoin, while the toy car on the table, played with by the little boy, symbolizes carbamazepine. Notice the lab-stuffed toy decorated with flowers? Flowers can easily be associated with Valentine's celebration. So Val represents valproate, and the little boy's mother's top points to topiramate. Finally, the lamb on the table held by the mother represents lamotrigine. These drugs, each with its unique mechanism, work together to help manage seizures and improve lives. Another mechanism of action of antiseizure drugs is by increase in inhibitory neurotransmitter activity in the CNS. This occurs following binding to GABA-BZDCL channel complex. This can occur either by increase in GABA mimetic and GABA facilitatory action in the CNS. Examples of drugs exhibiting this action include diazepam, clonazepam, phenobarbital, etc. By now, we're familiar with objects used to symbolize recurring features. The set of identical twins representative of a clone symbolizes clonazepam, the dying cat symbolizes diazepam, and the fern leaves atop the gazebo symbolizes phenobarbital. Something important about this image is the plus at the top of the gazebo. The mechanism of action of this group of drugs is to enhance the act of GABA, an inhibitory neurotransmitter symbolized by the street sign in the image. The plus symbol will help you associate this mechanism of act with this image. It is important you recognize this pattern, as we'll be using a similar approach in the coming scenes. Picturing a nerve terminal in horizontal direction will facilitate your understanding of the arrow illustration in the next scene. Drugs like gabapentin increase the inhibitory neurotransmitter activity in the CNS by increasing the release of GABA in the neuronal terminal. Notice the forward-pointing arrow at the top of the gazebo in this image. You can mentally visualize a nerve terminal and associate the forward arrow as increased release of GABA. Take note of the GABA signpost too. The large pen in the gazebo symbolizes the drug in this class, gabapentin. In this scene, we're still exploring the mechanisms of anti-seizure drugs. Here and in future videos, we'll use cooking as a metaphor for metabolism. Just as a chef builds up and breaks down ingredients, metabolism involves the transformation of neurotransmitters. So whenever you see a chef's representation, think metabolism. Now let's focus on a specific mechanism. Some drugs increase inhibitory neurotransmitter activity in the CNS by decreasing the metabolism of GABA at the neuroeffector junction. This is like a chef carefully preserving the flavor of a dish. An example of a drug that works this way is vigabatrin, symbolized by the bat in the image. Take note of the GABA signpost and the chef's hat on top of the gazebo. These visual cues will help you remember this concept. The bat, with its keen senses, represents vigabatrin's ability to precisely target GABA metabolism, promoting a balancing effect in the CNS. Other drugs like tiagabine increase the inhibitory neurotransmitter activity in the CNS by decreasing the reuptake of GABA into the neuronal terminal. Again, notice the GABA signpost? A group of people are having a tea party. Tea sounds like tiagabine. That should help you remember that tiagabine carry out its anti-seizure effect using this mechanism. Take note of the backward arrow at the top of the gazebo and the GABA signpost. It is representative of the action of this drug to decrease reuptake of GABA into the terminal. Before we proceed, let's recap. We have seen that anti-seizure drugs can act by 1. Inhibition of NA channels. 2. Increase in inhibitory NT activity in the CNS, either by increasing GABA mimetic or GABA facilitatory action in the CNS, by increase in the release of GABA in the neuronal terminal, e.g., gabapentin, by decrease in the metabolism of GABA at the neuroeffector junction in the CNS, e.g., vigabatrin, or by decrease in the reuptake of GABA into the neuronal terminal, e.g., tiagabine. Next, we'll explore how some anti-seizure drugs work by decrease in the excitatory NT activity in the CNS and capture it in memory with the image in the background. Major excitatory NT in the CNS are glutamate and aspartate. Glutamate acts by stimulating metabotropic or ionotropic receptors in the CNS. Stimulate metabotropic receptor GPCRs and ionotropic receptors, kainate, NMDA and AMPA receptors. Valproate inhibit excitatory activity at NMDA receptors, while topiramate inhibit excitatory activity at kainate receptors. This scene takes place in a glue factory. Glue rhymes with glutamate and serves as a pointer to one of the excitatory neurotransmitter. The asphalt road behind the glue factory, which is seen through the window, symbolizes aspartate, the other excitatory neurotransmitter in play with these drugs. Glutamate stimulates metabotropic receptors. Metabotropic receptors is represented by the chef in the image. Recall metabolism, metabotropic chef. The chef is holding an iron with a can labeling. The iron represents ionotropic receptors also stimulated by glutamate, while can is a mashup of the types of ionotropic receptors. K for kainate, A for AMPA, and N for NMDA. Now focus on the lady. She's wearing headphones and smiling at her phone writing. She's listening to a funny voice note. Voice note can be abbreviated as VN. This should help you remember that valproate inhibit excitatory activity at NMDA receptors. Also notice her chef's top with the word mate on it. Top and mate have been consistently used throughout this video series. The TikTok logo on her phone, together with top mate, should help you remember topiramate inhibit excitatory activity at kainate receptors. Let's dive into this scene to decode the intricate mechanisms of anti-seizure medications that involves inhibiting slow CH2+ T-type channels in the thalamic neurons. In this image, the bridge symbolizes the thalamus, the relay center of our body. Much like this bridge serves as a relay between 2 points. Now, focus on the small Volkswagen car being cleaned by a young man. This brand is peculiar for its slow sped. The car represents the slow T-type calcium channels, the car LCM channels, vital in the thalamic neurons. In the corner, we see a young pale girl, arms stretched out, holding a basket. On the floor beside her is an earthen pot filled with fern leaves and a sock. Together, these symbolize ethosuximide, one of the drugs that inhibit these slow calcium channels. The pale young girl, almost ghost-like, symbolizes the oscillatory ion channels implicated in the pathophysiology of absent seizures. Pale, absent. These channels are essential targets in the treatment of absent seizures. At the center of the scene, adjacent to the girl, there are 2 lambs and a bottle of wine. The lamb is bout recurring symbol for lamotrigine, while the bottle of wine stands for valproic acid, both of which are crucial in the inhibition of these channels. Now that we've UDEF-stood this scene, let's recall. The bridge, a symbol of oscillatory ion channels, helps us understand how these slow calcium channels in the thalamus play a significant role in absent seizures. The drugs that inhibit these channels, ethosuximide, fensuximide, valproate, and lamotrigine, are symbolized by the various elements in this scene. Remember, the slow Volkswagen car represents the slow T-type calcium channels, central to the treatment of absent seizures.